Hello, sir. My name is Parvin, and this is the explanation for the assignment given to us. Okay, the first question is the derivation of the bending force equation, assuming that the casing is not in a continuous contact with the well bore. So, see this. Okay, the first step that I did is that to determine the deformation. So the deformation can be determined using either the inner or outer portion of the pipe. As per the drawing here, we can see that the outer portion is under tension and the inner portion is under compression. So the change in the elongation is as given here, which is delta L over L. The same will be obtained if we use the inner portion of the pipe. So the the delta L can also be expressed as the R plus y2 delta Dirichlet severity or angular deformation minus with the radius of curvature delta angular deformation, which gives us y2 delta angular deformation. So using the Young modulus as the base formula, we can deduce that the Young modulus is equal to stress over strain, the change of stress over change of strain. So we can express the change in strain as delta stress over the Young modulus. So if we see here, we can actually combine this equation with this particular equation here, giving us this equation number 1, where delta L over L is equal to delta stress over Young modulus. And this can also be explained as delta stress is equal to Young modulus multiplied by y2 over radius of curvature. 1 over r is the radius of curvature. So moving on, so we want to express this in terms of the bending force. So what we do is that stress is equal to force per unit area. So the bending force can be deduced as the area multiplied with the change in the stress, which is given by equation 2. Now substituting equation 1 into equation 2, we can obtain the following equation here, which is bending force is equal to area of the pipe section multiplied by the Young modulus multiplied by y2 over r, which is the radius of curvature. But what we want is in terms of field units, so we convert the all the parameters given here in field units, where the y2 is expressed in terms of inches, so we divide it by 12, and the radius of curvature is given in terms of radian over 100 feet, so we multiply it with pi over 180, giving us the equation 3. So now assuming that y1 is equal to y2 as per our previous drawing here, y1 equals to y2, we can deduce that the y1 equals to y2 is actually equals to the diameter of the pipe divided by 2, and the nominal weight can be given as 3.46 multiplied with area of the cross sectional of the pipe. So the equation 3 can be rewrite in form of these unknowns here, which is the diameter and also the nominal weight of the pipe. So the bending force is equal to when we do the simplification, nominal force over 3.46, Young modulus diameter over 2 over 12 multiplied with radius of curvature and the conversion to radian, we will be obtaining 2.102 times 10 to the power of negative 6 multiplied with nominal weight, Young modulus, diameter, and the angular deformation. So now, since all the pipe is considered steel, see, we take the Young modulus as 30 times 10 to the power of 6 psi, and just substitute it into this E here, and we will be obtaining this equation number 4. So but the equation number 4 can only be used if the pipe is in a continuous contact in the well bore. However, this is not true in real life operation due to 3 main factors. The first thing is that the borehole is usually irregular, it doesn't have a uniform diameter, And another thing is the casing is run with centralizers, so the casing is not completely in contact with the reservoir. There are centralizers to keep it with a gap from the well bore, and the inconsistent radius of curvature as well. So to derive for the non-continuous contact of the pipe, the radius of curvature is given in terms of moment, or we can call it as torque, and Young modulus, and also the moment of inertia. So 1 over r is the radius of curvature given in terms of torque or moment over Young modulus times with moment of inertia, which is equation 5 here. And the moment of inertia for a cylinder can be defined as pi over 64 outer diameter power 4 minus inner diameter power 4. So assuming a small bend section, the radius of curvature can be expressed in the second derivative in order to give the slope. So 1 over r is equal to d2y over dx squared, which is equation 6. So when we substitute the equation 5 into equation 6, we will be obtaining d2y over dx squared equals to moment over Young modulus times with moment of inertia, which is equation 7. Now considering this drawing here to actually depict the moment in the pipe, we can see that the main moment is here, which is the ms, and then we have small horizontal moment here, which is weight of the pipe x sine theta, and also the vertical component here is weight of the pipe x cos theta here. So as we can see here, now from this figure we can express the moment, the total moment experienced by the pipe is equal to the moment here, which is the ms, plus with the y component and the axial force, plus with the x component and the weight force acting on the bottom part here, minus with the small component, the vertical and horizontal and vertical component here. However, the vertical and horizontal component as expressed here is quite small, so we actually neglect it, giving us the equation mx is equal to ms plus with the vertical component and also the horizontal component. And by substituting equation 7 into equation 8, we can obtain that d2y dx squared is equal to the moment of inertia, the total moment is actually substituted with equation 8 here, over Young modulus times with moment of inertia. So we can actually simplify this by bringing this particular term to this side. So d2y over dx squared minus axial force in the direction of y over moment of inertia and Young modulus is equal to 2 times delta stress over E d naught, which is from the previous derivation that we did, and Fwx over moment of inertia times Young modulus. So simplifying it, we can actually express Fa or the axial force over moment of inertia times Young modulus as psi 2 or psi squared. So by substituting this, we will be obtaining this equation here. After obtaining this equation here, we will integrate the above equation. So when we integrate it in with respect to y, so y is equal to 1 over psi squared multiplied by 2 delta stress max over Young modulus diameter multiplied with hyperbolic cosine psi x minus 1 plus with f over psi cube ei hyperbolic sine psi x minus psi x here. So moving on to the next. Now by taking the boundary conditions, so since we integrated it, we have a few constants that need to be described here. The first, so we're going to have two boundary conditions here. The first boundary condition is there is no pipe to wall contact, because that's what we assume, it's not a continuous contact with the valve bore. So d power 3, which is the third derivative of the y component, y and x component, gives us the equals to 0, and the midpoint of the joint is parallel to the borehole. So dy over dx is equal to half of radius of curvature. So by applying all these boundary conditions to the integrated equation, we can see that the radius of curvature can be written in form of this equation here. So by rearranging the equation in terms of stress, maximum stress, we can obtain E over diameter over radius of curvature, psi over 2, hyperbolic tangent, psi lj over 2. And when we rearrange this, we will be getting this equation 9 here. So by substituting equation 9 and equation 4 together, we can simplify it further to give us the bending force is equal to AS, which is the area of the cross-sectional area, times with the delta stress, maximum stress. So AS E diameter, angular deformation over 2 lj, psi lj over 2, 1 over hyperbolic tangent psi lj over 2. And when we combine all this and solve it, we'll be getting 63 nominal weight of pipe, diameter, angular deformation 6 psi lj over hyperbolic tangent into 6 psi lj, which is the value of which is the equation or the final derivation equation that we wanted. Now moving on to the second question. So the second question actually requested the critical analysis of whether the given factors will affect the collapse and burst resistance directly or indirectly. So moving on to the first case, which is the casing strength. So the casing strength is expressed in terms of the minimum yield strength of the casing itself. So casing is exposed to burst pressure when the internal pressure is higher than the external pressure. So this creates a net pressure causing a burst, and the collapse pressure occurs when the external pressure is higher than the internal pressure, causing a net pressure pushing the pipe inwards. So using the Barlow equation, we can see that the burst pressure rating of a pipe is a direct function of the minimum yield strength of the pipe itself. So the burst pressure is directly proportional to the YP, and the collapse pressure is the same, is directly proportional to the YP. So since the burst strength of the pipe is directly proportional to the minimum yield strength of the pipe, hence the casing strength directly affects the burst and collapse resistance of the pipe. So it directly affects for the casing strength. Now moving on to the second factor is the bending force. So bending force occurs when there are two axial forces acting on the pipe, on the upper side where the compression and the lower side is the tension. So stress at the outer diameter of the pipe that causes bending can be expressed as stress of the bending is given by Young modulus diameter over 2 times radius of curvature. So the bending stress contributes to the equivalent axial force given by the equation below, which is force due to bending is Young modulus multiplied with pi over 360 diameter alpha over L and pipe cross-section area. So the bending force contributes to the axial force component in the triaxial envelope. However, since the burst and the collapse resistance falls under the radial stress component, the bending force contributes indirectly to the burst and the bending pressure. This may happen when the bending force contributes to the equivalent axial force that exceeds the pipe strength and jeopardizes the minimum yield strength of the casing, since the pipe bending can lead to tension on the high side and compression on the low side. So what happens is that the bending force doesn't directly affect the minimum yield strength of the pipe. However, it affects the minimum yield strength by imposing some axial force component onto the pipe itself. So bending force is an indirect relationship with the burst and collapse resistance. Now moving on to the suspended weight. The suspended weight, when the pipe is immersed in a drilling fluid, the weight of the pipe is reduced by the buoyancy force. So this is taking into consideration the real case scenario where in the well we have the drilling fluid supporting the weight of the casing as well. So the axial force contributed by the suspended weight of the casing is given by force or the weight applied by weight imposed by the weight of the pipe in the air minus with the buoyancy force acting from the bottom of the pipe. So the suspended weight contributes to the axial force component in the triaxial envelope. However, since the burst and collapse resistance falls under the radial stress component, the suspended weight of the casing contributes indirectly to the burst and bending pressure. Once again, this axial component actually contributed by suspended pipe. If it exceeds the minimum yield strength of the pipe, the burst and collapse resistance of the pipe will be jeopardized. Again, same as the bending force, the suspended weight doesn't directly affects the burst and collapse pressure. However, it affects the tension, or it can impose tension on the pipe, which actually changes the minimum yield strength of the pipe, causing it to have a lesser resistance to burst and collapse. Now, the third one is the shock load. This is the fourth one, the shock load. So shock load happens when the casing is subjected to acceleration. For example, when we run in hole and the slip suddenly closes it, so we have acceleration, and when this occurs, there is a compressive strength wave generated in the pipe body. So this wave actually travels from the slip all the way to the bottom, then return back to the slip. So what happens is that the strongest is generated at the center, and this can be simply explained using the momentum equation, where the shock load can be defined as impulsive force times with time. Again, this shock load also contributes to the axial loading component of the pipe, and when the axial loading is high enough to exceed the minimum yield strength of the pipe, the burst and collapse resistance of the pipe will be reduced. This is an indirect relationship, since the shock load does not contribute directly to the radial load component except for the area at the slip. However, this can be regarded because the compressive strength exerted by the slip itself is not a function of the shock load. The shock load is due to the acceleration and not due to the forces, the radial force exerted by the slip. And the drag force. Drag force usually occurs when the pipe is reciprocated or rotated during landing or cementing. So the drag force can be defined as the negative friction factor multiplied with the modulus of the normal force. So in a highly deviated well, which is very common nowadays, so the drag force actually provides a major contribution to the axial loading component in the load design parameters. So when the axial force exceeds more than a specified pipe strength, strain can take place. And what happens is that when strain takes place, the thickness of the pipe can be reduced when there is tension applied. So what happens is that the minimum yield strength of the pipe will be jeopardized. So this reduction in minimum yield strength will in turn affect the burst and collapse resistance, causing it to be lower. So this is also an indirect relationship, since the minimum yield strength is not a direct parameter in the drag force calculation. So to actually summarize this, question 2 can say that only the casing strength has a direct relationship with the burst and collapse resistance. The bending force, the suspended weight, the shock load, and the drag force has an indirect relationship with the burst and collapse resistance, because all these four actually contributes to the radial to the axial component of the triaxial stress. So that's all from me. Thank you.